Hello everyone, my name is Mark Hauser with Friends of the Chicago River, and today I'd like to take you on a virtual field trip into Chicago River chemistry. As part of Friends' mission to improve and protect the Chicago River system for people, plants, and animals, Friends runs the Chicago River Schools Network to help students monitor the river and look out for its health into the future. Student education and water quality monitoring is but one aspect of Friends' work. If you'd like to learn more about the other things we do, please visit our website. Today we will be visiting the Chicago River at West River Park on the north side of Chicago at the confluence of the North Shore Channel and the North Branch of the Chicago River. This is a site where the Army Corps of Engineers removed a dam in 2018. The dam's removal has improved water quality, hydrology, and biodiversity in this section of the river. However, it is still heavily impacted by channelization, combined sewer overflows, and litter. Today we will be testing 9 different parameters of water quality and getting an overall water quality score. Before we do that though, I want you to take a minute and just think whether you think the water's quality is going to be excellent, good, fair, poor, or very poor. We will be doing our water quality testing from a dock extended out into the river. As the camera pans around, you'll be able to see the North Shore Channel and the North Branch of the Chicago River. So our water quality samples will include a little bit of water from each. Today we'll be performing tests for phosphate, pH, nitrate, dissolved oxygen, biological oxygen demand, change in temperature, total dissolved solids, turbidity, and fecal coliform. We'll talk about some of the sources of these pollutants, the importance of doing the test, why we do it, and then actually show you how we do the test and then talk about our results. Chemistry is a science, and so we'll be using units. A lot of the water quality tests have different units associated with them. One of the more common ones is ppm, or parts per million, also called milligrams per liter. For freshwater chemistry, they are essentially the same and they'll be used interchangeably in this video. It's also worth noting that some tests are better if they're higher and some are better if they're lower. For example, dissolved oxygen, you want a nice high level. But for phosphate and nitrate, some of the nutrients, you want a nice low level. Water chemistry testing is a snapshot of water quality on the day you do the testing. So for context, the river here hadn't received much rain for many days, the flow was moderate, and there hadn't been any reported combined sewer overflows or bacteria. Not all of the water quality tests are weighted the same either. By far, the dissolved oxygen and fecal coliform, or bacteria levels, are the most important factors in determining water quality. Far more important than, say, turbidity or total dissolved solids. We're about to start the 9 water quality tests here in just a second, but I wanted to give you one last look at the river. And again, think of that question as whether you think the water's quality today is going to be excellent, good, fair, poor, or very poor. Every river, depending on its depth and flow rate, will have a natural fluctuation in temperature during the seasons. However, what we're really looking at is a drastic change in temperature over a very short course of a river. Sustained high temperatures decrease oxygen levels and promote bacterial growth. Heat pollution, short-term large temperature gradients in a very short period of the river, shock animals and decrease biodiversity. Sources of some of these high temperatures can be discharges, particularly from power plants, and a lack of shade in a river, especially if it's a shallow river. Cold water under 13 degrees Celsius is suitable for large fish and insects. Your moderately hot rivers are suitable for smaller fish, but also allow a lot of non-native species and bacteria to grow. And your hotter rivers are pretty much lethal to larger fish and many aquatic insects. To record the change in temperature, the first thing we did was to take the temperature about a quarter mile upstream of the dock where we did the rest of the testing. When we used an alcohol thermometer, we got a temperature of 22 degrees Celsius at this location. When we repeated the temperature reading down at the dock later, we also got 22 degrees Celsius. Turbidity, or suspended solids, are the larger physical particles that are in your water sample. Generally, they come from soil erosion and organic material like algae and other plants. Excess sediment and other physical particles can impede breathing in animals with gills. It impedes filter feeding and blocks and absorbs sunlight, therefore raising the temperature of the water and reducing photosynthesis. To sustain aquatic life, a 10-day average of turbidity should not really exceed 25 NTU, with no single reading exceeding 50 NTU. If you're wondering what NTU actually stands for, they're nephelometric turbidity units, which you don't really need to know to do the test, just kind of keep an eye on the numbers and watch those. There are several different ways you can measure turbidity. Today we'll be using a Secchi tube, which is a long 120 centimeter clear plastic tube that has a Secchi disc down in the bottom extended from a string that you can manipulate up and down to get your level. Simply fill the Secchi tube by holding it under the water, pointing the opening in the upstream direction. Allow it to fill all the way to the top, and then take your reading. You get your reading by manipulating the Secchi disc up and down by using the string until the disc itself is just barely on the edge of your vision, looking straight down through the tube. We can just see the disc at 58 centimeters down in the tube. The water level at the top is at 3 centimeters. By subtracting the 3 centimeters at the top from the 58 centimeters at the bottom, we find we can see through a water column that is 55 centimeters tall. Whereas turbidity are your larger particles in water, total dissolved solids are the small ones that don't fall out of suspension when just left alone. They can include sodium chloride, potassium from road salt, fertilizers, and other chemical compounds. Dissolved solids in water can upset chemical processes, impeding breathing in animals with gills, upsetting cellular structure and metabolism, and decrease reproduction success. To sustain aquatic life, dissolved solids shouldn't exceed 150 parts per million. To measure total dissolved solids today, we'll be using a probe, electrical conductivity probe. First, we will turn it on. Then we make sure it's simply calibrated to read parts per million for natural freshwater bodies. We stick it in the water and press the hold button. And our total dissolved solids reading is 502 parts per million. Possibly one of the easier tests to understand is pH. How acidic or basic the water is can be caused by acid rain and mining activities. It's worth noting that here in Illinois, low pH or acid is buffered by the presence of limestone and dolomite in our bedrock. It acts like a huge antacid tablet underneath us. pH is indicated by the number of free hydrogen ions in the water. Too high, alkaline, or too low, acidic, will preclude many forms of life from living in the water. Most people, plants, and animals thrive in water with a pH between about 6.5 and 8.2. The pH scale is logarithmic. In other words, 2 is 10 times higher than 1, 3 is 10 times higher than 2, and so on and so on. pH does not have units, it's just simply a number. 7 is neutral. If you are drinking water, you would want it to be a 7. The lower numbers are the acidic numbers, and the higher numbers are alkaline. For this test, we get 2 test tubes of 5 milliliters of river water each. We place both test tubes in the black comparator and insert the color wheel, which will indicate the pH. We add the indicator solution, which will turn one of the tubes a color which will match to the wheel. We hold the comparator up to a light source, turn the wheel, and we find that our pH is 7.5. If you take vitamins, you'll understand these next pair of tests. Nitrates and phosphates are like vitamins for plants. They help them grow. They are in every plant, and they are released when that plant dies. However, humans also put chemicals on plants to help them grow, fertilizers and things like that. These nutrients, like nitrates and phosphates, promote plant growth, and if in excess because of fertilizer runoff, can cause hypoxia, a decrease in oxygen, and eutrophication, which is killing fish and reducing biodiversity. Now you'll notice the two chemicals are actually on a different level. Phosphates, it only takes a part per million or 2 to be harmful, whereas with nitrates it takes several dozens of parts per millions to be harmful. But they both promote plant growth in and out of the river. First, the nitrate test. Again, we obtain a water sample and add our reagents. We then compare it to the blank tube and get our reading from the color wheel. Once we get a color match, we obtain our result, which turned out to be 2.3 parts per million of nitrate. Next is the phosphate test. Once again, we obtained a water sample from the river and added our reagent.
Be careful, you call them back. That's enough. Come back over here.
We placed the treated water and the untreated water in the black comparator with the color wheel. Once we get a color match, we obtain our result, which turned out to be 1 part per million of phosphate. If you've ever taken a deep breath, you'll know about our next test. Humans breathe oxygen out of the air. Aquatic organisms breathe oxygen out of the river. But they're both the same compound, O2. Oxygen is breathed by aquatic animals, and the more the better in the water, up to 100% saturation, just like for us on land. Oxygen is the byproduct of photosynthesis. It's created by plants and mixed into the air when water is in motion through riffles or waves. The EPA suggests that the lower limit to sustain fish is somewhere around 5 parts per million, but the more the better as long as it's less than 100% saturation. Saturation is a good point to think about because you can absorb different amounts of oxygen in different temperatures of water. The hotter the water, the less oxygen you're going to be able to dissolve in it. Colder temperatures, you'll be able to dissolve more oxygen. We obtain a sample from the river by using an enclosed dissolved oxygen bottle. We then add reagents to turn the oxygen from being a gas in the water to being physically part of the solution. We add the last reagent and thoroughly mix to turn the solution a bright, shiny yellow. The last step is to perform a titration in which 1 drop of an added solution is going to equal 1 part per million of oxygen. Until the solution turns clear, then we obtain our answer. You can actually count along as we count the number of drops it takes to turn the solution clear.
One. 2. 3. 4. 5. 6.
7, 8, 9, 10.
As you can see, it took 10 drops to turn the solution clear. Therefore, we had 10 parts per million of dissolved oxygen in our sample. This was at 22 degrees Celsius, which gives us a percent saturation of about 113%. The first 7 tests that we've just done, we were able to do at the river on the day that we were there. The last 2, biological oxygen demand and fecal coliform, are multiple day tests. And so we gathered our samples that day, but I'll be sharing videos of us getting our results on other days. The first test is biological oxygen demand, which is actually a measure of the amount of oxygen used by aerobic bacteria as they break down waste particles, organic waste in the river. Polluted rivers with lots of organic matter use up a lot of the oxygen through decomposition. And so to obtain our BOD reading, we use our dissolved oxygen reading that we just got on day 1, and we gather a sample, we take it home, and do it again on day 5, and whatever the difference between the two is our biological oxygen demand reading. High levels of organic material, including leaves, dead fish, garbage, industrial waste, fertilizer, pet waste, and other sewage, will raise BOD levels and make them unhealthy. Generally, the cutoff is 5 parts per million. A change of more than 5 parts per million in the oxygen level will be a bad or poor biological oxygen demand reading. Anything less than that, and it's much better water quality. The sample for the biological oxygen demand test has been sitting in a room temperature, dark place for 5 days since we came back from the river. No oxygen has been added because the sample's been in a sealed container with no interaction with the atmosphere, and any plant material has been unable to do any photosynthesis because we kept it in a dark place. We simply repeat the same procedure as we did with dissolved oxygen 5 days ago at the river. If you look closely, you'll see the solution is not as yellow as it was when we were at the river. So we will expect to see less oxygen in this sample. Let's see how many drops it takes to turn the solution clear. You can count along if you wish. One, two, three. As you can see, it took 3 drops to turn the solution clear. We subtract that 3 parts per million from the 10 parts per million we got 5 days ago, and biological oxygen demand comes out at 7 parts per million. The other test that we have to perform back at home is fecal coliform, or E. coli, or bacteria. Fecal coliforms are bacteria, though not pathogenic themselves, are indicators for the presence of human feces in the water, and thus the potential for the presence of other pathogens. They're caused by leaky septic systems and combined sewer overflows, which are untreated sewage that is being released into the water that can contain fecal coliforms. To be safe for swimming, there should be no more than 200 colonies per 100 milliliters. To be safe for boating, generally should have no more than about 1,000 colonies per 100 milliliters. To perform our fecal coliform test, we're simply going to gather a sample of river water, in this case 5 milliliters, and introduce it to a growth medium, which we will then take back home and plate on a petri dish. Poured the samples out into a petri dish, allowed it to solidify, and then incubated it upside down for 24 to 36 hours, depending on the temperature. After incubating for 36 hours, bacteria colonies appear as either white, pink, teal, or purple dots. We determine fecal coliform, or our E. coli reading, by counting the purple colonies. We count 9 per 10 milliliters, or 90 colonies per 100 milliliters. Now that we've completed all 9 of our water quality tests, let's look to see how we calculate an overall water quality score. Here is our water quality data. Each test result has its own distinct units. To combine them all into a water quality score, we must calculate a Q value for each test. A Q value is a number from 0 to 100 based on the quality of each parameter or test. The higher the Q value, the better. 100 is the best, 0 is the worst. It's a way of standardizing all the different water quality test results so that they can be combined and used to find an overall water quality score. First, locate your test value on the x-axis. Determine where that value intersects the curved line on the graph and follow it horizontally across to the y-axis to find out what your Q value is for that test. So what are our Q values for turbidity and total dissolved solids? Turbidity was 55 centimeters, which converts to 9 NTU. That gives us a Q value of 78. Total dissolved solids was 502 parts per million, which is off the edge of the chart and converts to a Q value of 20. Let's look at the Q values for pH, nitrates, and phosphates. For pH, the value was 7.5, that's a Q value of 93. For nitrates, it was 2.3 parts per million, that's a Q value of 95. And phosphates were 1.0 parts per million, that's a Q value of 40. Determining the Q value for dissolved oxygen is a two-step process. First, we take a straight line and connect 22 degrees Celsius at the top with 10 parts per million at the bottom. The line crosses the middle at 113% saturation, which gives us a Q value for dissolved oxygen of 94. Lastly, the Q values for biological oxygen demand, change in temperature, and fecal coliform. For biological oxygen demand, the change was 7 parts per million, which is a Q value of 46. Change in temperature was 0 degrees Celsius, that's a Q value of 93. And fecal coliform was 90 colonies per 100 milliliters, which is a Q value of 42. Let's enter each of the Q values into our chart. Note that none of the Q values have any units. Finally, we multiply each Q value by that test's weighing factor. The weighing factor is how important the test is to the overall water quality score. Note that dissolved oxygen and fecal coliform are weighted the most, and turbidity and total dissolved solids are weighted the least. Finally, we add up the subtotals and get an overall water quality score of 68.35 and a water quality index of fair. At this time, I'd like you to reflect on what you thought the water quality was going to be for this river. Turns out for this location, on the day we did the testing, we got a water quality score of 68.35 out of 100, which gives us a water quality index of fair. Whether or not this is a score that you were anticipating, it could have been worse, and there is definitely room for improvement. If you would like to learn how you can improve the river's water quality, please visit chicagoriver.org.